Welcome to today's Explainer. Today, we are fundamentally shifting how we look at our planet. You know, when you stand on a beach, it's so easy to just see a pretty view, right? Maybe a place to get a tan or catch some waves. But we aren't looking at a giant swimming pool today. We are looking at a massive, dynamic, completely interconnected engine that literally drives planet Earth. Everything from the crazy weather you experience, all the way down to the very air you breathe, is governed by the mechanics of this system.
To truly appreciate the scale of this engine, consider this absolute mind-bending statistic. A staggering 99% of the Earth's entire biosphere, meaning the total volume of space where life exists on this planet, is contained entirely within the ocean. Think about that for a second. Every dense forest, every jungle, every mountain range, and every single city combined makes up just that tiny 1% sliver.
Sure, you've probably heard that the ocean covers about 71% of the Earth's surface. But surface area is only half the story. Because it has depth, it provides 96% of the Earth's actual living space. It's a vast, three-dimensional world that completely dwarfs our existence up here on land, holding an incredible 80% of all living organisms on Earth.
So, here is our blueprint for today. First, the scale of our ocean. Second, mapping the ocean floor. Third, temperature and salinity. Fourth, the ocean in motion. And finally, why the ocean matters.
All right, kicking things off with part 1, the scale of our ocean, and setting the baseline.
Moving right along to part 2, mapping the ocean floor, the architecture beneath. Okay, let's dive right into this. If we really want to understand the ocean, we have to understand the physical hardware it sits in. And let me tell you, it is far from just a flat, featureless bathtub. As you move off the land, you transition through the continental shelf, dropping steeply down the slope and rise until you hit the vast, sweeping abyssal plain. But the real drama? That happens at the tectonic boundaries. Notice the stark contrast here. At divergent boundaries, where tectonic plates pull apart, we get massive underwater mountain chains called mid-ocean ridges. Conversely, at convergent boundaries, where plates crash together, the seafloor literally plunges into dark, freezing trenches. And dotted all across these plains are towering underwater volcanoes known as seamounts and flat-topped guyotes, right alongside deep submarine canyons carved heavily into the continental margins. It's wild down there.
Coating all of that dramatic architecture is a layer of oceanic deposits created through incredibly slow sedimentation. We can neatly group these into 3 distinct categories to make it easy. First, lithogenous sediments. These are your muds and wind-blown dust coming straight off the land. Second, we have biogenous sediments, and these are the remains of life, things like corals and fine biological oozes. And third, hydrogenous deposits. These are things like evaporites and metallic nodules, which actually precipitate directly out of the water chemistry itself.
Which brings us to part 3, temperature and salinity. Basically, the chemical operating system of the ocean. So, if the basin is the hardware, heat and salt are the chemical operating system that actually runs the ocean engine. Let's look at how heat is distributed horizontally. Because temperature isn't uniform at all, it's dictated by 4 main factors. Latitude is the big one. Temperature naturally decreases as you move towards the poles because insolation or sunlight decreases. Makes sense, right? Then there's land and water distribution. The northern hemisphere actually receives more heat because it has way more land mass to absorb it. Prevailing winds also push surface water around, causing deeper water to cycle up or down in what we call upwelling and downwelling. And finally, ocean currents distribute this heat globally. Interestingly enough, out of all the world's oceans, it's actually the Atlantic Ocean that records the highest average temperature.
Now, what's really interesting about this is how things change vertically. The upper layer of the ocean is obviously the hottest, getting baked by the sun, and that heat transfers downward through convection. But as you descend, you hit 2 major transition zones. The thermocline is a boundary region where temperature drops off an absolute cliff, decreasing rapidly with depth. In contrast, the halocline is the transition zone where salinity, the saltiness of the water, increases rapidly as you go deeper.
And speaking of salinity, which we measure in parts per thousand, it's highly dynamic and tightly controlled by 4 main surface variables. The rate of evaporation versus precipitation is basically the master dial here. If more water evaporates than falls as rain, the ocean gets saltier. Simple as that. But this is carefully balanced by the amount of fresh water flowing in from rivers, the wind velocity, and again, those massive ocean currents mixing it all together.
All right, part 4, the ocean in motion. Let's talk about waves, tides, and currents.
With our hardware and operating system firmly in place, let's look at the engine actually in action, starting with waves. It is vital to remember that waves are not just moving water, they are energy moving through the water. Step 1. Wind contacts the surface. Step 2. Friction transfers energy from the air directly into the water molecules. Step 3. The stronger the wind, the longer it blows, and the further the distance it covers, the taller the wave becomes. Now keep in mind, this is entirely different from a tsunami, which is a massive wave triggered not by wind, but by sudden underwater explosions, earthquakes, or landslides.
To really put that wind energy into perspective, check out this geographical fact. The absolute largest wind-driven waves on Earth occur right in the Indian Ocean, regularly reaching 7 to 14 meters in height. That's massive. Why? Because in this specific region, the winds blow in the exact same direction, at a totally constant speed, over a massive distance. That setup allows that energy to just build and build and build.
Next up, we have tides, and these operate on a much more cosmic scale. Tides are driven by the gravitational pull of the moon and the sun on our spinning Earth. When the moon, Earth, and sun are perfectly aligned in the straight line, their gravitational pulls combine to create what we call spring tides, which are almost 20% higher than normal. But when they are out of alignment, pulling at competing angles, we get much weaker tides, known as neap tides, resulting in considerably lower high tides.
So the crucial point here is that these celestial mechanics have profound practical impacts right here on Earth. Tides are incredibly significant for human civilization. They're absolutely crucial for coastal navigation. They act as a giant natural flush, cleaning out sedimentation from estuaries. We're actively learning to harness them to generate clean electricity. The constant movement even helps keep polar harbors ice-free during those neap tides. And of course, the cyclical high and low tides heavily aid coastal fishing communities around the globe.
Finally, we have ocean currents. Think of these as massive rivers flowing within the ocean itself, and this brilliantly illustrates their planetary impact. Take a look at the western margins of continents. The presence of cold currents there actively aggravates arid, desert-like conditions on land. In fact, this exact mechanism is responsible for the Atacama, the Namib, and the Mojave deserts. But on the flip side, where cold currents and warm currents collide and mix, they churn up tons of nutrients, creating the absolute richest, most abundant major fishing grounds in the entire world.
And finally, Part 5, Why the Ocean Matters, or the engine's ultimate output.
We've seen the sheer scale, the structure, the chemistry, and the motion. Now let's look at the engine's output. The ocean provides monumental ecosystem services and resources for us. It acts as our primary global heat sink and climate buffer, absorbing massive amounts of heat that would otherwise make the surface completely uninhabitable. It supplies critical industrial resources through mining, offering up oil, gas hydrates, and those polymetallic nodules we mentioned earlier. It drives a multi-billion-dollar tourism industry, sustains global fisheries, and crucially, acts as a primary generator of oxygen.
Let's put a human face to those fisheries for a second. Ocean fisheries support over 170 million jobs worldwide. For tropical developing countries, the ocean provides a staggering 60% of their population's dietary protein. This isn't just an ecosystem, it is quite literally a global food engine.
But perhaps the most profound output of all is this mind-blowing fact straight from our source material. Ocean plants, specifically phytoplankton, produce almost half of the oxygen we breathe. Every second breath you take, right now, as you listen to this explainer, was manufactured by microscopic plants drifting in the upper layers of this incredible water engine.
We are entirely, totally dependent on the continuous, healthy operation of the ocean. It regulates our climate, it feeds our populations, and it literally fills our lungs. So, knowing that it provides the very oxygen we breathe and buffers our climate against extremes, the ultimate question is, how will humanity step up to manage and interact with this intricate, beautiful engine in the future? Thank you so much for exploring with us today. Keep questioning and keep learning.